Assalamualaikum and good day to all of my students. Today we're going to continue our discussion for the past year question, February 2025. So let's have a look at the question 3. The question states that a steam power plant operates on the reheat Rankine cycle and has a net power output of 80 megawatt. Steam enters the high pressure turbine HPT at 10 megapascal and 600 degrees Celsius and enters the low pressure turbine at 2 megapascal and 500 degrees Celsius. Steam leaves the condenser as a saturated liquid at a pressure 0.010 megapascal. The isentropic efficiencies of the high pressure turbine and the pump are 80% and 95% respectively. For this operation, the changes in kinetic and potential energies are negligible. Using the inlet for the pump as state 1, sketch the cycle on a single TS diagram and determine the moisture quality at the low pressure turbine LPT exit, the network output in kilojoule over kilogram of the cycle, the thermal efficiency in percentage of the cycle, and the mass flow rate of the steam in the system in kilogram per second. So the first thing that you need to do once you receive this question is, first one is to read the question, really understand what I've been given by the questions, and then what you need to do is to list all the given properties, all the given informations from the questions. So these are the items that has been given by the questions: P3, T3, P5, T5, P1, and also the state at state 1, which is has been stated as saturated liquid. You also can draw the TS diagram, but at this stage it's just a draft of the diagram. So as being shown in this TS diagram, this is representing the reheating process, okay, where we have high pressure turbine state 3 to 4 and also low pressure turbine state 5 to 6. Next, what you need to do is for you to characterize, okay, especially for state number 4 and state number 6. So we want to know exactly which phase are these states are. So if we do the characterization for state 3, we are going to get it is in superheated state, yeah, just like the figure that has been given here. So you can find the properties, enthalpy and entropy for state 3 from table E6. Also at state 5, if you do the characterization, yeah, it is in superheated state, then you can find the enthalpy and also the entropy for state 5 from table E6. Right, so given at state 1 is saturated liquid with a given pressure of 0.010 megapascal, and if we convert it into kilopascal, we are going to get 10 kilopascal. So from this you can determine the enthalpy and also the specific volume at state 1. Then you can obtain it from table A5, referring to the properties with subscript F. Next, what you can do is that you find all the enthalpies, all the necessary properties from the remaining states. So previously we have state 6, 5 and 1. So now we are going to find for the remaining state 2. So we know that state 2 having the same pressure as state 3, which is 10,000 kilopascal or 10 megapascal. So for state 2, we know that in order for us to determine the enthalpy, we are going to use the isentropic relation between the work pumped in, where we know that work pumped in can be in these two relations. Thus, from these relations, you can obtain the enthalpy for the isentropic processes between state 1 and state 2. And being given from the questions is the isentropic efficiency for the pump, which is 0.15. Thus, you can determine the enthalpy for the actual at state 2 by using the isentropic efficiency formula. So please refer to your appendix if let's say you forgot the formula, so you can refer to your appendix, and please ensure that you really understand what is being listed in your appendix, so that it will be easier for you to answer the question. Next, we are going to go to state 4. So state 4, the pressure will be the same as the pressure at state 5. State 4 is leaving your high pressure turbine, entering your regenerator. So the pressure will be the same with state 5, which is entering our low pressure turbine, which is 2 megapascal. If we convert it into kilopascal, then we are going to get 2000 kilopascal. So for this, we know that the process, okay, for the ideal case will be isentropic with state 3. So entropy at state 4 is equal to entropy at state 3. So previously we have determined the entropy at state 3. So based on the pressure and the entropy values, you can do the characterization, and then you are going to get over here at state 4, it is in the superheated phase. So state 4, if we look into this diagram shows that state 4 is in the mixture phase. So since from our characterization, it is shown that state 4 is in the superheated phase, thus what you can do is that you need to amend state 4 so then it will be in the superheated phase. Okay, like this. So this will be 4S, and this will be 2S and 2A. This will be 4A, and this will be 6A. Alright, so then now you know state 4 is in superheated phase, thus you can find the enthalpy for the isentropic process H4S from table A6, referring to the pressure, and you find the range, okay, the location of the entropy as 4. So for this state 4, you might need to conduct interpolation because the entropy lies in between certain figures. Once you have done the interpolation, then you are going to get the value for the H4S. Alright, so in the question given to you is the isentropic efficiency for the high pressure turbine, which is 0.8. So that meaning you can determine the actual enthalpy at state 4 H4A based on the isentropic efficiency formula for the turbine. So next is for state 6. We know that state 6 will have the same pressure as state 1, which is 0.010 megapascal, which is equivalent to 10 kilopascal. So at state 6, for the ideal case, we know that the entropy for state 6 will be the same as the entropy at state 5. So when you do the characterization later, you are going to find out that at state 6, it's in the mixture phase, saturated liquid and saturated vapor mixture phase. So for this, since you have the entropy, so now you can determine the quality at state 6, and after that, based on the quality, then you can further determine the enthalpy at state 6. Alright, so please note that from the questions only give you the isentropic efficiency for the high pressure turbine, but state 6 is actually leaving your low pressure turbine. So for this, we cannot determine the actual enthalpy because we doesn't have the informations on the actual sites. Alright, so previously you have determined the quality at state 6, so you're going to get 0.905, which is you are going to, this will be the answer for the item A. Then you are going to need to find the net work out in kilojoule over kilogram. So work net out, we know that will be equal to work out minus work in. So this is Rankine cycle with reheating. So we have two work out, okay, from the high pressure turbine and also low pressure turbine, and then minus with the work in from our pump. So you're going to get this value. So next is item C, which you need to determine the thermal efficiency. So we have the work net out just now, so now you need to determine the Q in. Okay, so Q in also will have 2. So please remember to sum or to add these both Q in from our system or cycle. Right, so if you forgot what is Q in and everything, so let me show you here. So state 2 to 3, this will be the first Q in. State 4 to 5, this will be another Q in regenerator. So exiting our high pressure turbine HPT state 3 to 4, so this will be the first work in, and state 5 to 6 process through the low pressure turbine, this will be another work in. Right, so once you have substitute all the required necessary value, then you are going to get the answer is 41.2%. Okay, so given to you in the question is the work net out, power net out, W dot net out 80 megawatt. So 80 megawatt is equivalent to 80 joule per second. So if we convert into kilojoule per second, so you're going to get 80,000 kilojoule per second. So in order for us to find the mass flow rate, so then you need to divide it with the work net out, then you're going to get straight away the mass flow rate m dot equal to 52.73 kilogram per second.